Welcome, folks, to the site of a very familiar race, just like we had done the last time. We're going to take our red train that we saw in the previous video and our black train, the slower of the two that we also saw in the previous video, and let's watch them race again. However, this time we're going to take the data that we find, and instead of looking at it mathematically, we're going to look at it through a graph. On your mark, get set, go. Pretty clearly, the red train won the race. But more interestingly was where I had the race stop. I had this race end at exactly 140 centimeters. We knew from our last video that the red train covered 140 centimeters in exactly 5 seconds. And in those same 5 seconds, our black train only traveled 82 centimeters. 5 seconds passed for both trains. The red train, though, covered 140 centimeters, while the black train only covered 82 centimeters. Let's now switch over to our board so we can take a look at what this looks like on a graph. Hello, folks. I'm Mr. Pinola, and now let's take a look at the main focus of our video today, graphing motion. We're going to do that by creating what's called a distance versus time graph. A distance versus time graph shows us where an object is after a certain amount of time has passed. So let's now see if we can plot the motion of both the red and the black train on the distance versus time graph. We're going to start off by plotting the motion of the red train. Now, our red train, we know, covered a distance of 140 centimeters in 5 seconds. However, we want to focus on where the red train was after 1 second, 2 seconds, 3 seconds, 4 seconds, and 5 seconds to really give us a sense of what the graph looks like. Now, it was kind of hard to see from the video that we started with today. However, I took some careful data about where the red train was after certain amounts of time. After 1 second, our red train covered exactly 28 centimeters worth of distance. So I'm going to plot that data point on my graph. After 1 second, it covered about 28 centimeters worth of distance. After 2 seconds, the red train had covered 56 centimeters worth of distance. After 3 seconds, the red train covered 84 centimeters worth of distance. After 4 seconds, it covered 112 centimeters worth of distance. Notice how it keeps traveling further after each amount of time. That makes sense because it keeps getting further away from the starting point or further away from the origin. Lastly, after 5 seconds, as we already said, the red train covers an ultimate distance of 140 meters. That's because it is now, after 5 seconds, 140 centimeters, away from the origin. We can very clearly tell that the red train is covering the same amount of distance every second. In fact, each second, the red train is moving 28 centimeters. That makes sense if you remember our last video, because we found the speed of the red train to be 28 centimeters per second. Let me now connect the dots to show the real motion that the red train is experiencing. Notice that this does not mean that the red train is moving uphill. Instead, it just means that every second, the red train is covering the same amount of extra distance until it ultimately reaches 140 centimeters in 5 seconds. But let's now take a look at our black train on the same graph. And our black train did not cover quite as much distance as the red train. In fact, in 5 seconds, the black train only covered 82 meters. And so once again, I took some data about how far each of these trains would move after certain amounts of time. I found the black train after 1 second only covered about 16.4 centimeters worth of distance. After 2 seconds, the black train covered 32.8 centimeters worth of distance. After 3 seconds, the black train covered 49.2 centimeters worth of distance. After 4 seconds, 65.6 centimeters worth of distance. And as we all know, after 5 seconds, 82 centimeters worth of distance. Now, both trains started from the origin, a position of 0 meters at a time of 0 seconds. So let me make this dot for the red train. We know the red train was at 0 meters after 0 seconds had passed, and so was the black train. And now I'll go back and connect my points for the black train, just as I did for the red train. Once again, you're going to notice the same type of pattern as the red train. It's a line going upwards. The black train was moving across the table. It was not moving uphill. So a line that is slanted upwards on a distance versus time graph does not mean that the object is going uphill. Instead, if you have a straight line, sort of like both of these lines are, that just means that you're covering the same amount of distance every second. For the black train, every second that it moved, it covered a distance of 16.4 centimeters. That makes sense because if you remember from our last video, the black train had a speed of 16.4 centimeters. But let me prove this to you. We're going to take a moment to figure out the slope of each of these two lines. Let's start with the red line. If I wanted to find the slope of this red line, I could use rise over run, the formula that some of you might be familiar with for slope. Well, let's pick 2 points that happen to be on our line. Here's a point. This point is located at 2 seconds, 56 centimeters. And let's take another point just a little bit further up the way. This point is located at 3 seconds and 84 centimeters. Let's find the rise, which is how much the line goes up from one dot to the next, and divide it by the run, or how far across it is from one dot to the next. In this case, notice that the run went from 2 seconds to 3 seconds. From 2 to 3 seconds is a difference of 1 second. So the run is equal to 1 second. Then for our rise, we went from 56 centimeters all the way up to 84 centimeters. If we subtract those two numbers, we can do that using our calculator, we will find that the rise is equal to 28 centimeters. Calculating the slope for the red line would just mean that we have to do the rise divided by the run. Or in other words, 28 centimeters divided by 1 second. Well, guess what? 28 divided by 1 is 28. And our units are centimeters per second. Wasn't that the speed of the red train that we found in the last video? What you're noticing is something really important, and that is that the slope of a line on a distance versus time graph is equal to the speed of the object. Clearly, the red train experienced had a speed of 28 centimeters per second, and the slope of the line for the red train is exactly 28 centimeters per second. Let's do the black train as well. I'm going to pick two random points. Let's choose this point, which is 1, 16.4. And let's also pick this point. This point is 4, 65.6. And once again, we will do our rise and our run. To find the run, we went from 1 to 4 seconds. That's a difference of 3 seconds. So the run is 3 seconds. For the rise, we went from 16.4 all the way up to 65.6. Let's take out our calculator and subtract those two numbers, 65.6 minus 16.4, and our rise is equal to 49.2 centimeters. That's how much the line went up in the y direction. Well, we'll find slope just the exact same way that we did for the red line, by doing rise divided by run. In this case, the rise is how much the line went up, 49.2 centimeters. And the run is how much the line went across in between the two dots that I selected, which is 3 seconds. I'm going to do a little bit of math here. 49.2 divided by 3. That gives me an answer of exactly 16.4 centimeters per second. Interesting. That's the exact same number we came up in the last video. The black train moves at a speed of 16.4 centimeters per second, which is exactly equal to the slope of its line on the distance versus time graph. Just as the red train moved at 28 centimeters per second, and that was the slope of its line on the distance versus time graph. If a line on a distance versus time graph has a big slope, it is moving at a fast speed. And if it has a very low slope, then it is moving at a very slow speed. Now let's take a look at a slightly different example. We're going to change things up slightly by taking a look at this simulation. Watch what movement the man makes when I hit the play button. Man moved forward for about 4 seconds, then he stops for a couple seconds, and then he continues moving, but at a faster speed until he reaches 10 meters, which is to the right of this house. Let me show you that motion one more time. Here we go. 3, 2, 1. He moved to the 4-meter mark, stopped, and now he's moving faster until he reaches the 10-meter mark. This motion is a little bit different than the motions that we just looked at from the trains, and that's because the man is not moving at constant speed. He's changing his speed. He's not keeping the same speed the whole time like the toy trains kept. At one point, he was moving slow at the beginning. Then he was, in fact, moving 0 for a little bit because he was at rest. And then he was moving fast towards the end. But did you know that we can show speeds that are changing on distance versus time graphs as well? Let's take a look at how to do that. Welcome back to the board as we analyze the motion of the man we just saw on a distance versus time graph. We're going to do it the exact same way that we did for the moving trains. We know that the man in the simulation you just saw took exactly 4 seconds to move a distance of 4 meters. Notice the distance is in meters now, not in centimeters, so I've changed my axes to reflect that. So after 4 seconds, the man has moved a distance of 4 meters. Now we could break down how far he had moved after each amount of time. For example, after 1 second, he was at 1 meter. After 2 seconds, he was at 2 meters. 3 seconds, he was at 3 meters. But we already know that the line is going to be straight during the first 4 seconds of his motion because the man was moving at a constant speed. And a straight line, even though it might be diagonal on a distance versus time graph, shows us that the object during that time has not changed its speed. So let me draw this line in. A nice straight line during those first 4 seconds. In fact, at 0 seconds, the man was located at a position or a distance of 0 meters. So I could technically include this first point as well. However, then the man did something interesting. He didn't continue moving at this same speed, and he stopped and stayed at 4 meters for another couple seconds. So after 5 seconds passed, the man was still at a position of 4 meters. After 6 seconds passed, the man was still at a position of 4 meters. Notice when I connect the lines now what I have. Now my line is flat. Do you know what the slope of any flat horizontal line is? If you said 0, you'd be right. This line is a slope of 0, and that means the man is moving at 0 meters per second. In fact, during this part of time, he is at rest. But then he continues moving. In fact, for the last part of his motion, he continues to move at a constant speed, but a faster constant speed than before. And ultimately, after 3 more seconds, which would give us 9 seconds, he ends up at a position of 10 meters. We can break that down. After 7 seconds, he was at a position of 6 meters. After 8 seconds, he was at a position of 8 meters. And after 9 seconds, as I already drew, he was at a position of 10 meters. Let me connect those dots. You'll notice I made a small mistake. I put this one a line too low, so just ignore this extra blue dot over here. Notice the slope at the beginning of the man's movement compared to at the end of the man's movement. This line at the end is very steep. It has a big slope, and that means the man was moving at a fast, constant speed at the end of the problem. And he was moving at a slower constant speed at the beginning of the problem. That matches what we saw in the simulation itself. So this distance versus time graph does not show a man climbing a hill. It shows a man moving at a slow constant speed, then stopping to rest for a couple seconds where the line is flat, and then continuing to move further from the origin, but moving at a faster constant speed, as indicated by the steeper line. Let's take a look at one last motion. I'm going to hit play and you're going to see a car moving across your screen. Watch its motion closely. Let's show that one more time. Notice that the car moved with a constant speed, but then stopped in the middle of its motion. Then it turned around and moved with the same exact constant speed back to where it originally came from. This is another tough situation to put on a distance versus time graph, but we can still do it. Even though the object turned around and changed directions, we can still show that on a distance versus time graph. Let me wrap up this video by showing you how. Welcome back to the whiteboard as we graph the motion of that car you just watched. Now, it may have been hard to notice from the simulation because it went by so fast, but this car was moving at constant speed for the first part of its motion. In fact, it traveled exactly 15 meters in the first 5 seconds after starting at the origin. So it started down here, and then after 5 seconds, the object had traveled a distance of 15 meters. We know that the first part of the car's motion was done at constant speed, and so therefore I can use a single straight line to show that motion. If I wanted to, I could find the car's speed during this time by finding the slope of the line. However, that's not my focus right now. Instead, I'm going to continue graphing. And that's because the car continued to move in this way. It then rested for 1 second, which means that at 6 seconds, it was still at 15 meters. Then it moved back, and ultimately, after another 5 seconds, and I'm going to put 11 seconds here on my diagram, because that would be 5 seconds later after 6 seconds. At 11 seconds, it didn't continue moving further away. In fact, it was back at a distance of 0 because it went back to the origin. So at 11 seconds, I'm going to put another dot down here, indicating that the car has gone back to its original distance, which was 0. And so I'll make sure I label my origin 0 as well. During that last part of the motion, the car also moved with constant speed. So we can use a single straight line to represent that. And so notice what we have. This is not a diagram showing a car going up and down a hill. No. Instead, this is a diagram that shows a car moving at constant speed away from the origin, then the car resting for 1 second, and then the car moving at the exact same speed as it was before, back to its original position. The reason we can say that the speed over this first part of its motion and the speed over the last part of its motion are the same is because the slope of the line is the same in each case. Even though this slope is down and this slope is up, neither line is steeper than the other one. And therefore, we can see that the car was moving with the same speed as it went out to 15 meters, as when it came back from 15 meters in the last part of its motion. I hope you learned something in this video about distance versus time graphs. You should come back with a couple takeaways from them. We noticed that the slope of a line on a distance versus time graph represented the speed. And that meant that when we had a line that had a bigger slope, the object was moving with a faster speed during that time. We also noticed that when the line was flat, that the object was at rest during that time. And lastly, as you saw from our last example, if the object switches from moving upwards in the graph to moving downwards, that just means that it has changed direction. We are not discussing objects climbing hills in distance versus time graphs, but instead we're looking at how the object's speed and direction changes. Next time, we'll look at distance versus time graphs a little bit closer.